And if you adjust your r square in this way, that means when your r square is actually adjusted by, sorry, so this is 1 minus summation ui hat square divided by summation yi minus y bar whole square, and then if you adjust by corresponding degrees of freedom, then we will get, this is called now r bar square or adjusted r square. This is called adjusted r square. So when we say adjusted r square, this is adjusted for degrees of freedom. Okay, so adjusted r square adjusted for degrees of freedom. Okay, adjusted for degrees of freedom. Now we can compare r bar square or adjusted r square of two different models involving different number of explanatory variable. Absolutely no problem here. Once you adjust with degrees of freedom, the r bar square or adjusted r square of the two models are easily comparable. Okay, easily comparable. So while r square is not comparable across two different model, r bar square is. That is one thing we have to keep in mind. And what is the relationship between r bar square and r square? See, r bar square equals to 1 minus, you can easily understand, 1 minus r square into n minus 1 by n minus k. Okay. So from here, because r square equals to 1 minus sum of ui hat square divided by summation yi minus y bar whole square. So if you put this into here, then you will get a relationship like this: r bar square equals to 1 minus, this would become, this entire thing will become 1 minus r square. So 1 minus r square, and this would become n minus 1 by n minus k. Okay. So from this relationship we can understand two different cases. Let us say case 1, when r square equals to 1, then what will happen? This would become 0, and r bar square is also 1. That means r bar square equals to r square. Case 2, when r square equals to 0, then what will happen? And k is also greater than 1, we can say that r bar square is actually negative. Okay, r bar square may become negative also. That means while r square lies always between 0 and 1, r bar square may become negative when r square equals to 0. Of course, that is a very, very rare possibility that in a model r square equals to 0, but theoretically this is also possible. In general we can say, in general r bar square is actually lower than r square for k greater than 1. Okay, this is the relationship. That means as additional variable included in the model, r bar square increases less than r square, and that is what we actually want. We need to give a penalty, we need to give a check to balance the R square out of this lower degrees of freedom. So, this is the relationship between R bar square and R square. Now, the question is, among these two goodness of fit measure, which one is best? Econometrician, they say that nothing is called better than the other one, rather we need to report both these R square as well as adjusted R square when we compute the model. For example, when you estimate the model, if you look at then your model is actually giving R square as well as adjusted R square, and you see adjusted R square is always lower than the R square. From here also you see R square equals to this and adjusted R square is actually 1.1528. So, adjusted R square is lower than this one. So, this is how we can actually get the adjusted R square measure by adjusting its degrees of freedom if at all we want to compare the explanatory power of two different models, right, two different models. Then one more thing that we must learn in multiple linear regression model, that is called overall significance. Overall significance. So, when we are running this model, child mortality rate equals to beta 0 plus beta 1 FLR plus beta 2 PGNP. This is our model. Okay. And how do we compare, how do we check the significance of this beta 1 hat? The significance of beta 1 hat, we say that following the confidence interval approach, we say that we will construct an interval and we will say that probability beta 1 hat 1 hat minus T alpha by 2 into standard error of beta 1 hat, standard error of beta 1 hat less than equals to beta 1 less than equals to beta 1 hat plus T alpha by 2 into standard error of beta 1 hat equals to 1 minus alpha. So, we will construct the interval and we will see whether the interval captures the hypothesized value of the true population parameter. That is how we check the individual significance of the variable. Similarly, for beta 2, we say that beta 2 hat minus T alpha by 2 into standard error of beta 2 hat less than equals to beta 2 less than equals to beta 2 hat plus T alpha by 2 into standard error of beta 2 hat is also equals to 1 minus alpha. So, this is by confidence interval approach, and we can also check the significance by T statistic. You look at the calculated T statistic of FLR and PGNP and compare the tabulated value, and we decide whether the variable is significant or not. Now, the question is, can we decide? So, that means here what was our null hypothesis? Null hypothesis was beta 1 equals to 0, and in this case our null hypothesis is beta 2 equals to 0. But now, when we talk about overall significance of the model, let us say that our null hypothesis is beta 1 equals to beta 2 this becomes 0 or not. This is our null hypothesis. For testing overall significance of the model, this is our null hypothesis. That means what we are saying, combinedly FLR and PGNP do not have any significant impact on child mortality rate. So, obviously, we can understand one thing from this model. If we have already tested the individual significance of the variable following the t statistic or this interval approach, what is the necessity of putting this null hypothesis once again? Can't we say, conclude anything about this on the basis of the individual significance of the variable? Okay? That is the question that we are asking here. Alright. What is the question we are saying? That individually we have tested the significance of beta 1 and beta 2. Then what is the need of testing the combined significance of beta 1 and beta 2? Can't we say that since these variables are individually significant or insignificant, they are jointly also significant or insignificant? The answer is no. We cannot decide about joint significance or overall significance based on individual significance. What is the reason? The reason we can understand clearly from the confidence interval approach. When we construct the confidence interval for testing the individual significance, okay, while constructing confidence interval for testing individual significance, we assume implicitly what we assume, that these intervals are estimated based on a different sample, that the intervals are estimated from different sample. However, they are not. When we test the joint significance, that means based on this probability statement, we cannot say that beta 1 hat plus or minus t alpha by 2 into standard error of beta 1 hat, this interval and this interval beta 2 hat t alpha by 2 into standard error of beta 2 hat, these two intervals will capture probability that the intervals this and this capture beta 1 and beta 2 simultaneously is not 1 minus alpha square, 1 minus alpha square, that we cannot say. Okay, please try to understand what I am saying. So, if we try to infer something about overall significance based on the individual significance, that means indirectly what we are saying, that probability this interval will capture the true population parameter beta 1 is 1 minus alpha. Probability this interval will capture the hypothesized value of the true population parameter is 1 minus alpha. But that does not mean that these two intervals jointly capture the true value of beta 1 and beta 2 is 1 minus alpha square, because these two intervals are actually not independent. These two intervals are not independent, they are constructed based on the same sample, and that is why we cannot infer anything about the joint significance based on the individual significance. So, in terms of this diagram, let us say that this is our T distribution for T1, this is distribution for T1, and then distribution for T2 is actually, if we say this is not the case, okay, if this is the case, then we could have said that just because of individually they are significant, jointly also variables would be insignificant, because the probability statement that the intervals capture the true population parameter 1 minus alpha square is valid if and only if these two distributions are independent. Rather, in reality, what happens, if this is your T1, then T2 also like this, this is T1 and this is T2, and this is the overlapping area, because these intervals are constructed based on the same sample. That is why individual significance or insignificance, I will write, does not confirm about overall significance, overall or joint significance. For that, so that means for overall significance we need to have a several different statistic. Overall significance requires a different statistic, and that is F. If you recall, initially we said that when you estimate the model, the data will supply two different type of statistic, one is T, another one is F. So, when you have only one explanatory variable in the model, T and F, we cannot distinguish their role. But when you have multiple variable in your model, that means in the context of multiple linear regression model, T and F, their role is different. While T, they indicate individual significance, F in that context will give you the overall significance of the model. Okay, and how is this F statistic defined? If you estimate the model from our ANOVA table, what we get from our ANOVA table, what we get? We get ESS, we get RSS, right? Now, if we take a ratio of this ESS and RSS adjusted by their degrees of freedom, then this F is equals to actually ESS by its degrees of freedom, and then RSS by its degrees of freedom. Okay, degrees of freedom, and that will follow an F distribution with degrees of freedom for the numerator and denominator, whatever is specified. Okay. So, now if we go back to our example, So, when we take this model, this is our complete model, this is our complete model, and we look at the ANOVA table. What is model sum of square? The model sum of square value is this 2,57,362.373, and what is the degrees of freedom? Is 2. Okay, because the degrees of freedom for the ESS is defined as TSS minus RSS. TSS is 63 because total number of observation is 64 and RSS is 61. So, 63 minus 61 is actually 2. Okay, is 2. So, how is this F defined then? These models, if you take a ratio of this MS. So, how is this MS? MS is basically SS by its degrees of freedom. So, we have 2 MS, right? We have 2 MS, and if we take the ratio of these two, so that means MS for the first and MS for the second, then we will arrive at the F value, and what would be the value? This value would be 73.63. Okay, that is nothing but this 1,28,681 divided by 1,742. If we take a ratio of this, that will give you our F statistic. What would be the degrees of freedom? Degrees of freedom would be 2 and 61. So, 2 and 61 in this particular case. So, that means we need to first define the degrees of freedom for the ESS, degrees of freedom for the RSS, and then we will get. Okay? And that basically, then what we need to do? We need to compare this. This is called F, calculated F, and then we need to compare this calculated F with the tabulated value. And if the calculated F is greater than tabulated F at, let us say, 1% or 5% significance, then we have to reject H naught. And what is the H naught? H naught was beta 1 equals to beta 2 equals to 0. Once this is rejected, we will establish the alternative. That means, yes, the variable, they have their joint significance also. But we need not compare the F value with the tabulated one, as we said earlier. If we go back with the P value, so the moment we estimate the model, your data is also reporting F value with corresponding P value. If you look at the P value is 0.0000. If you multiply that by 100, that will still less than 1. That means, we will say that our model is significant at 1% level. Okay? Our model is significant at 1% level. All right. In Stata, we have a specific command for implementing F-statistic, and the command is the test command. Test, you need to put FLR, and then you need to put PGNP, and then you can put 0. This is the test command for F-statistic. Right? Test command is a very, very powerful command. We can test the individual significance of the variable from this. So, if you estimate the model, once again, reg CM, PGNP, and then FLR, this is the complete model, and now you have to put the test command, test PGNP equals to FLR equals to 0. This is the command. If you put enter, then you see the data is also reporting you the F-statistic and the value is exactly same. So, what we have computed manually by taking ESS by its degrees of freedom, RSS by its degrees of freedom, and then ratio of that, the same value is arriving if we put test command in stata, and the value is 63.83 with the same degrees of freedom 2 and 61, and the corresponding F value is 0.0000. So, with this we can establish the overall significance of the model. So, by now then we have understood the importance of F statistic over the T. While T gives individual significance of the model, F gives you the overall significance of the model. And later on when we discuss about multicollinearity, there we will see in presence of multicollinearity, even if your variables are individually insignificant, you will see that still variables are overall significant. That means T statistics, they become unreliable in the context of multicollinearity, and we must rely on the F statistic to check the joint significance of the model. So, when the variables are significant, there is absolutely no problem, your overall significance will also be there, even though theoretically we cannot infer directly from individual to overall. Theoretically that is incorrect, but you will still get overall significance of the model. But in case of variables, most of your variables are insignificant, you will still get overall significance of the model in case of multicollinearity. That is how we need to understand this F statistic very clearly, which is basically a ratio of the two MS defined by ESS by its degrees of freedom, then whole divided by RSS by its degrees of freedom, the overall significance of the model. So, with this we are closing our discussion today, and next day we will discuss about some other important hypothesis testing in the context of multiple linear regression model. Thank you.